Hey TechKnowStuds! In our last video, we went over gates or logic gates. Logic gates allow us to have inputs into our circuit and then get some sort of output out of our circuit. And now what we can do is we can take those logic gates and assemble them and put them together to perform some sort of action. In this video, we're going to get into a half adder and how to create a half adder out of the gates that we learned in our last video. In one of my last videos, I showed you how to add binary numbers, at least just simple numbers, just single digit numbers here. So if you had an input of 0 and an input of 0, add that together and it would be 0. So 0 and 0 as the inputs would be an output of 0, and there's also nothing to carry here. So if you want to test yourself again, go ahead and pause the video and fill out the rest of the chart, and then press play and see how close you came to it. All right, so to go through this, 1 plus 0 was 1, so we have an output of 1, and there's nothing to carry with that. If we have 0 plus 1, we also have a 1, and there's nothing to carry with that. If we have 1 plus 1, 2 doesn't exist in binary numbers. So what we actually do is we reset this column, very similar to what we do in decimal, and then we carry a 1 to the next column. And there's a 1 in the next column now. So there's 1 carry bit and 0. So this is a chart of how we add two numbers together in binary. In another one of my videos, we figured out an AND gate, a OR gate, and a NOT gate. So if you want to, you can figure out these again, just to test to make sure you've got it down. So what I'm going to do is you can pause the video, try to figure these out down here, these tables out down here, and then play the videos to see if you got it right. And here's the answer. Feel free to pause the video and check your answers to see if you got it right. Now what we're going to do is we're going to combine the two concepts together and start figuring out how we can do gates, use gates in order to carry out this function of adding these single digits together. So what we're going to do is we're going to start out with the carry bit, because the carry bit is going to be the simplest out of the two here. This matches up with one of the gates that we already know that we have. So which gate is that? So go ahead and pause the video if you need to, but answer the question on what gate are we going to use right off the bat in order to come up with these outputs right here when these are the inputs. Now, if you came up with the solution of an AND gate, you would be correct, because this and this needs to be 1 in order to get an output of 1. And that's what we see right here. It's going to be 0 as the output unless both are 1. So that's the beginning of our half adder, is that we just need an AND gate. The next step of this is actually quite a bit more challenging. So only do this if you want to have some fun and play around with this. It's not necessary for us to move on and learn other concepts, but it is, like I say, I enjoy this stuff. It's like little puzzles that you can figure out. So if you're up for the challenge, go ahead and go through this process. If not, you can skip ahead to the answer and jump to that. So if you're wanting to figure it out, what I'm going to do is I'm going to give you some clues, give you some hints, give you some directions. You can try to figure it out. And then if you can't figure it out, you can hit play again, and then you can try to figure out, I'll give you another hint, and then you can try to figure it out again, and then I'll tell you what the answer is. But what we're doing is we've already created this carry bit. We've got this AND gate right here. We've got our inputs into the AND gates, which is these inputs right here. And it gives us that carry bit as an output. So we've got this part figured out. But what we haven't got figured out is this right here. So we need to figure out what this looks like. I'm going to give you part of the answer. We're going to start out with an OR gate, because the OR gate is going to get us close. The OR gate has an output of 0, 1, 1, 1. So this gets us close, but the problem is that this is off right here. So there's two gates that we need to add to this to get this as being the actual output. So down here, you can say this is the final output, and the input into this scenario is right here and here. And what is going to be that final output is going to be what we're trying to get out right there. And so you're going to try to figure out what goes in between these two. And there's going to be two gates. So what two gates do we need down here to get this answer right here? And so try to figure that out. I'm going to give you a little bit to play around with that. So go ahead and pause the video. If you want a hint, go ahead and press play and I'll give you a hint. All right, time for a hint. I cleared out some of the markings here so we could better understand this. What I'm going to do is I'm going to mark this as output X. We don't really care about what output X is because in the long run, it's not really part of this circuit. But what we're going to do is we just want to add that for clarification to see what this ends up looking like. So I'm going to fill in this extra column right here. And output X is just a simple OR gate. So the answer for this one is going to be 0, 1, 1, 1, given that these inputs over here. So that's what it is. So we essentially want this output right here to match what output X is for the most part, except for the case right here where the carry bit is 1. So essentially, we want it to match X unless the carry bit is 1. In that case, we want to make that 0. And there are two gates that you can put in here to make that happen. Now, I acknowledge that this is a little more complicated and quite a bit more things to think through. So I'm going to give you one more hint. I've added one of the gates right here, which is the OR gate, which means that this on this side is going to be the reverse. So in other words, this is going to give an output of 1, except for when the carry bit is 1. When the carry bit is 1, that means that it depresses this and the output over here is going to be 0. So that gives us half the equation. We also said the output X right here. So if we were to add that column right there, 0, 1, 1, 1. And we pretty much said that the case in which we want the output to be 0 is when the output of the carry bit is 1 and also the output of the OR gate is 1. And so that's when it turns it to 0. So now see, what gate do we put right here? We'll put a big question mark right there. What gate can we put right there to make this happen? And you only have 3 choices and well, there's 2 inputs right here. So it narrows it down to an AND or OR gate. Which one do you think it is? If you said an AND gate, then you would be correct. So let's go through and see what this looks like. So in this first scenario, we're entering a 0 and a 0. So the input is 0, 0, 0, 0 for the inputs here. And what comes out on this side is 0. So the carry bit is 0, which is what we have right here. And on this side, same thing, output is 0. The other side of this NOT gate is 1, so now electricity can flow there, but this is still 0, so we get 0 as an output. So everything lines up there. Okay, next, our input is 1, 0, so we change the inputs to be 1 and 1. So now we've got 2 1 inputs. The AND gate still is 0, so we still get a 1 right here. That still allows electricity to flow over here. Now we get an output of 1 right there. And so now we have electricity flowing all the way down, and now the output here is 1. Now, if we were to reverse this, it doesn't really change any of these gates at all. The gates are still going to output the same thing. So now we get the same answer. So now we've made sure that was correct. We made sure that's correct. Now let's do our last one, which is a 1, 1. So input 1, 1 for this. Oops. 1, 1. Okay, now what we get here is we get a carry bit of 1. It's carrying it to the next level there. And so now it's 1 over here. This flips to a 0 here, and which cuts off the power here. And now we end up with a 0 down here, which is what we want. So now this has been confirmed. So we are good to go. That is an AND gate there. What we've just created is called a half adder. A half adder adds 2 bits together. So we can add 0 plus 0, 1 plus 0, 0 plus 1, and 1 plus 1. Those bits are now able to be added together. We've just proved that we can add 2 bits together. Now what we need is another half adder to add the next 2 bits, and another one to add the next 2 bits, and another one to add the next 2 bits. And actually, in reality, since we're carrying over 1 into the next column, or the potential of carrying over a bit into the next column, then we actually need a half adder for that as well. But essentially the same thing is we just link these half adders together to add this number now together. So in the end, what you would do is you would just link a bunch of half adders together to add 2 numbers together. And now what we've just done is we've created a calculator. Of course, we're really here to talk about CPUs and how CPUs work. There's actually a part of this CPU that does the adding, that does calculations. Used to be called the math coprocessor, but they've integrated it now into the CPU. So there are different parts, and as I mentioned, there are different people who start creating all these circuitries, and now we actually have just computers creating computers. There's computers that do the designing of these circuits to the point where somebody really doesn't have the full map, the full millions of different transistors now that make up these chips. So really, this is now the end result is what we get. And that's how the calculation happens. That's how the calculation works. And so by using these gates and how we calculate things, we can create pictures, we can create images on our screens, we can capture images, we can do all sorts of amazing stuff with this. And it's just incredible really of how it works. But it all boils down to those transistors and those little micro switches inside these microprocessors.